It is 2 minutes past 2 my time, and I believe it's probably the same yours as well, unless you're from outside the Eastern time zone. We've got almost 40 people here this afternoon, which is makes me feel good that somebody either, I'm going to take it that attendance to mean that actually we have got 40 people interested in the design of photovoltaic systems. And that's exactly what we're going to talk about today. We are going to focus on non-battery backup grid connected systems. There's other kinds as well, but the first one to learn is the non-battery backup grid connected. Those are the basics. We'll learn a lot of basics here. And if you we have a follow-up seminar, 2 hours on battery backup system design. There will be lots of math, lots of numbers, lots of things here. So if this is something you want to be able to look over again, be sure to download the slides at the end. There is no additional charge for that, and you'll get a PDF copy. And so if it looks like I can't spend lots of time explaining every equation, whatever, but this will be a legitimate design exercise with both the structural, wind load, and electrical business of the design of a photovoltaic system. I don't see where you're all from, and I can't even ask where you're all from, but I say welcome. And let's hope that it'll be a productive afternoon for everybody. One thing we need to be sure of, if you have a question, and we certainly can have dialogue, that's the whole point of this being a live show or a live presentation, but we need to do that through the Q&A. So please save the chat for communication back and forth between the host, PDH source, and yourselves. But if you have a question that you want to discuss regarding the material, please click it in the Q&A, and I'll be watching for any questions coming up and trying to respond as quickly as possible. The only bad question is the one you don't ask, because if it's a question that's going to be answered later on, there it's a question just popped up right now. If the question will be answered later, I'll just indicate that. So yes, I can see this question if you write it, absolutely. So just type it on in, and Nicholas, we're ready to go. So if all the answers are this simple, that should make it, well, hopefully, I guess you know what I'm trying to say. Okay, so let's move on. Let's see. First thing it comes to mind when somebody's considering a photovoltaic system is, aren't they pretty expensive? And well, the answer is, yeah, they used to be, but not anymore. If you look here at the module costs, and this is just the module, not the system cost, between 1976 and 2020, started back over $100 a watt back in 1975, 76, that time frame. In 2020, they were down to about 40 cents a watt or less, depending on the quantity you buy and what kind of modules and so forth. So what else has come down in cost by a factor of 300 since 1976? Certainly not the cost of housing. And by the way, this doesn't account for inflation either. So if you talk about 1976 dollars, then one would argue the cost came down even more. Okay, so here we have the main reason, not only that the cost has come down, but a lot of other things have happened, including reliability has gone up and so on and so forth. One way to compare solar with other sources is the so-called levelized cost of energy. And this comparison here was put together by the United States Energy Information Agency. Different people do these different ways, so give all these numbers a 10% plus or minus leeway. but it gives you roughly an idea of where various sources stand. So what we're talking about, levelized cost of energy, means if you build the facilities for generating electricity, how much will you have to charge for that electricity in order to get your investment returned over the life of the system? That includes maintenance, decommissioning, construction, and all that kind of stuff. What it isn't included in this is the environmental costs of these various sources, and the numbers would change significantly if we were to include, for example, the environmental costs of coal or even natural gas now with all the methane leaks. People are pretty concerned about. Okay, so again, I see a one came up in the chat box, but please, if it is a question you want to discuss with the group, please transfer that over to the question and answer. Okay, that's the one I'm going to be responding to. If you have a question for PDH source, that can go into chat and he'll handle it independently. Okay, so as you see, natural gas is still relatively inexpensive. Advanced nuclear is pretty expensive on a levelized cost of energy. So, I mean, forget about the issues of nuclear waste and so forth. And I don't mean to speak for or against nuclear, but the price says something that would explain why a whole lot of more nuclear plants are not being built right now, especially if you can build onshore wind for 2.6 cents a kilowatt hour, and even residential PV compared to the Northeast, it's less than half the cost of what you pay for electricity in Northeast. And it's about half the cost of what we pay for electricity here in Florida. So, you know, how could anybody not want this stuff at this point? Another interesting question about solar is, well, doesn't it take a lot of energy to make the solar? There's a couple of questions. Let's see what we got here. Let's see, any idea where offshore wind fits in this group? It's about twice the price of onshore wind, if I remember correctly. Let's see, what did we? Yeah, so it's pretty cost effective. It's a lot less expensive than, well, and coal power installations fall on the list. They're not on the list because nobody's building coal anymore to speak of, Dave. And clearly the environmental costs of coal, until it becomes a whole lot cleaner, but then the levelized cost is still going to be up because of whatever. So let's just say that people would be building coal-fired plants if the economics and the regulatory things were supportive, but it's not happening that way. So let's see, I'm going to click that and click that and click that so that we can start fresh on the questions. So I think some of these questions we're going to get we'll come to the answers. What happened here? Oh, the PV energy return on investment. Okay. How much energy does it take to make PV versus how much energy PV makes as a result of having been made in the first place? This is something that is also a measure with a lot of other sources. For example, corn ethanol is one where it's argued that the amount of energy you get back is about equal to the amount of energy that you put into it in the first place. You're just converting one energy source into another, but not getting a return. With solar, for example, though, you use a certain amount of kilowatt hours to build a kilowatt's worth of electricity, which you then install, and in about 30 years or so, that system might be slowing down a little bit. But the point is, in 2017, the energy return on investment was somewhere between 10 and 30. So if you can imagine getting 30 times more energy back than you expended in creating it, that means we can use photovoltaic generated energy in order to make more photovoltaics, which will then be used to make more energy and so on and so forth. So the only thing is the photovoltaic systems are probably not going to run for 24 hours a day. because there are only a couple of places on the planet where the sun shines 24 hours a day, and that's not for very long. So yeah, there's some issues about at night and all, but in terms of total energy made, the numbers are very favorable for most of the PV technologies. And in fact, the ones that make it to the market commercialized generally have very good energy return on investments. And in fact, the energy return on investment is increasing. It gets better every year because people improve the efficiency of the productions. Okay, and cells themselves are becoming more efficient. Back in 10, 12, 15 years ago, the efficiencies were in the neighborhood of 13%. They're now at nearly 20%. Now that is not a 7% improvement, folks. That is a 33% improvement because in fact, it's a 50% improvement, isn't it? If you're going from 13 to 20, you're kind of going like you're getting a third more. In any case, you now can put 2,000 watts on the same space that we could have only put 1,350. So that's probably the easiest way to look at it. These percentage things get a little confusing. So in any case, it's not just the cells, because the inverters and the balance of system energy costs are decreasing significantly. Inverters now, for the most part, do not have heavy transformers in them, lots of steel and lots of wire. They're very small. I mean, 125,000 watt inverter measures something like 3 feet by 1 foot by 1 foot. That's amazing, because it's electronic and very, very few pieces of steel. One person could lift one of these, whereas 20 years ago, lifting an inverter that big would took at least a forklift and sometimes a crane. So a lot of things are going on here. Here's another question came up. Let's see. With real estate skyrocketing last 2 years, are these numbers still? Well, you know, that's another interesting thing, because with rooftop solar, when I look around me, there's a whole lot of empty rooftops. And for me, that's real estate. And let's do something with it. But these are the costs of installing solar. And regardless of real estate skyrocketing, the complicated part about the real estate is the weird roofs. I can tell you that I've reviewed plans for about 1,400 installations in the last 9 or 10 months. And some of the roofs out there are incredible. And it is absolutely amazing that you can put anything on these roofs, but it's being done and in large quantities. Typical average residential installation, somewhere 10, 11,000 watts. Let's see now. Done. Did that. Now, are there any more questions here? Okay, I don't think so. I don't know what happens when I say dismissed, but I'm just going to make sure I answer them and not worry about what that means. Okay, so things are getting better and less expensive. That's what's happening. What are the different types of photovoltaic systems? Obviously, you need to decide. You want a standalone, something like this, not connected to the grid. You might imagine where this one is. Look at that tilt. Feel free to type into the Q&A where you think this might be. And or you might want a grid connected system, something like this. Both of these are in the United States. And both of them are further north than Florida. So let's just see what some of the Q&A comments are and where you suppose these might be. Well, yep, got it right on Alaska. That's the entrance to the exit glacier on the Kenai Peninsula. And I guess you probably were clued in by the fact that this tilt was so steep. Of course, in Alaska, there's lots of sunshine in summer. And so there's a lot of PV. And furthermore, when it's colder, the PV works better than when it's hotter. So interesting about that. All right, good guess. The one on the right, by the way, that's up at Tucker Lake, New York, up at their nature center, and that was taken a long time ago. That's an old system, but it really impressed me when I first saw that up there. So I think, yeah, we're done here. I'm going back and forth too often to the Q&A. I'm going to hit dismiss and see if that puts them away. No dismiss questions. Okay, I can't do that. And it only says answered one. All right, I'm going to have to learn this a little better. Meanwhile, let's move on. Here's a couple examples of installations. This is kind of out in the middle of nowhere in Nevada. This is at Great Basin National Park. Utah has a few just kind of out there weather stations. You never believe that I kind of like traveling around the West, but there's a couple examples of some systems. But then again, Massachusetts loves PV. A lot of pretty nice systems installed up there. You can go up to the Yellowknife, Northwest Territories, Canada, and see what systems installed something like this. And these folks, electricity is fairly expensive up there. And then again, there's commercial rooftop PV. And of course, there's the utility scale stuff that gets up into the hundreds of megawatts range. Okay, well, let's talk a little bit about the sun, because after all, that's what we're depending on to make this energy for us. Peak sun intensity is about 1,000 watts per square meter. Okay, that's at sea level when sun's directly above. Depending on technology, about 20% of it can be converted to electricity. So that's about 200 watts per square meter that you can make. That if you're trying to figure out if you have enough area to accommodate the number of watts you need. And depending where you live, the annual conversion range is generally somewhere between 1,000 and 2,000 kilowatt hours per kilowatt per year. And of course, it depends on the system and the location. Albany, New York, the number is maybe a little more closer to 1,350. But there are a lot of places, even the relatively high latitudes, where we're looking at 1,500 kilowatt hours per kilowatt per year. Okay, and that's useful to know, because if you know your electric bill, then you'll know how many kilowatts you need to install in order to reduce your electric bill to zero. There are some very sophisticated performance models out there that can help you with this, and there's some that you can download for free. The one in particular that I like is the model that you can get from the National Renewable Energy Labs. It's called the System Advisory Model, SAM. And if you're interested in doing your own simulations, simply Google NREL-SAM, NREL-SAM, and download the program. And it's very intuitive. And within about 15 minutes, you are simulating. All you need to do is type in where you want the simulation in the weather and download the weather information for that area. And you can do some simulations. So let's talk about PV modules for a minute. These are things that make the electricity, and they have some very special electrical properties. For one thing, what's the best way to reduce the voltage of something to zero? Well, one way to do it is to turn the switch off. Another way to do it is short it out, because then the voltage across the terminals is zero. The current flowing through that wire might be a couple thousand amps, depending on whether it's battery or whatever, but with a photovoltaic module, and this particular one right here, which happens to be a 440 watt modern module, if you short these wires out when the sun is shining at full intensity, you're going to get about 11.6 amperes. And that's it. That's your short circuit current. If you measure the voltage across the terminals with them not being connected to anything, you get what's called the open circuit voltage. And you see that's when the current is zero. And you see for the 1,000 watts per square meter, the open circuit voltage is about 49.5, oh wait, about 49, okay? So there are four defining properties for modules that are important. The short circuit current, the open circuit voltage. Short circuit current is when the voltage is 0 and it varies with the sunlight. And the open circuit voltage is when the current is 0 and it also varies with sunlight, but differently than the short circuit current. I think it's pretty clear that the short circuit current varies pretty much linearly with the sunlight. As the sunlight gets twice as bright, the current becomes twice as much. The voltage, on the other hand, doesn't behave at all like that. In fact, it behaves according to the logarithm of the intensity of the solar. So yeah, even when the sun is not shining very brightly, there can be a lot of voltage across the terminals of a module. So you got to be a little careful with the module terminals. Of course, the connections, the leads on the modules have terminals that are shielded. So it's pretty difficult to get a shock from them because they're totally shielded. It's about like getting a shock from a light switch. What about IM and VM? Well, IM and VM, you can see that if you have, well, power is equal to current times voltage, right? So if you have 0 volts and 11.5 amps, there's no power being generated. If you've got 0 amps and 49 volts, there's no power. But somewhere in between there, as you go up the scale, 10 volts, 11 amps, there's 110 watts, 20 volts, 11 amps, there's 220 watts, keeps going right on up there, 330. And you just keep multiplying I times V as you go along that curve. And at some point, you find a point where it starts going down again. And that point where it maxes out is called the maximum power voltage. And it's characterized by a maximum power voltage and a maximum power current. Okay, so it's important because obviously if you want to get your money's worth with these modules, you want to operate them at their maximum power points. And there are some very clever electronic means that are being used in order to achieve that. It's much more obvious where the maximum power points are if you plot power versus voltage rather than current versus voltage. And you see that in this plot. And notice that the maximum power tends to be at about 80% of the module voltage, roughly in the 80% range. And notice that it stays pretty much at the same point no matter how bright the sun is shining. Now that's except for one thing, because there's another thing that's important. But first, let's talk about you connect these modules to something. They're going to be connected to an inverter or a charge controller. And most of the charge controllers and inverters these are connected to have electronic maximum power point tracking circuits inside of them. And they ensure that the maximum power is being delivered from the modules to the inverter. And of course, the inverter is what converts the DC from the solar to AC, which is more useful in general. So, but what happens as these modules get warmer or cooler? Well, we see that on this diagram here. And in general, the maximum power of the module decreases at about 0.36% per degree centigrade, which means if it operates at 25C, that's the standard test conditions. And you can see the maximum power there happens at about 42 volts, and it is roughly 440 watts. If we cool this thing down to 0 and still shine the full sunlight on it, we can get almost 500 watts out of it at a voltage of about 450. Whereas if it operates at 75 degrees, and that's not unusual for a module to operate 75 degrees down in the Mojave Desert or somewhere in any of the desert areas. And even in Florida, they get pretty hot, up to 70 or so. So therefore, as it turns out, modules almost never operate at their rated power because either the sun is not shining directly on them or they're heated above ambient temperature. And that's important when you get into the design of a system to recognize that if you have 5,000 watts of modules at standard test conditions, you're not going to get 5,000 watts out of that. And in fact, the most recent simulation I looked at for a New Jersey installation, the closest one would come to that was 83% of the 5,000 watts total rating for the array. So you can design your equipment with that knowledge that your inverter does not have to be as big as the power output of the modules, because they never get there. Okay, so, and even if they do, the inverter simply says, well, guess what? You're trying to give me 10 more watts than I want to process, so I'm just going to reject those 10 watts by bumping you away from your maximum power point. All right, so point here, though, is that clearly you need to in order to maximize the performance of the array, you want to keep it as cool as possible. And that's one of the reasons for mounting them above the roof with a little space underneath them, or even ground mounts where there's a lot of space underneath them, so that the breeze underneath, obviously it's going to be shaded underneath them. So that cools them down a bit. Whereas if they're integrated into the roof, then they're going to take full force of that heating of the sun. They'll run warmer, generally less efficient. Okay, so that's the main reason right here for mounting them above the roof, so they will perform more efficiently. So what about the orientation of the array? Because, you know, once upon a time, it was believed that if you didn't face that thing south, it was, you know, not worth installing it. Here you see a comparison for Albany, and if you look at 30 degrees facing south, this is a 30-degree tilt, that's where you get the most energy out of it over the year. But if you tilt it at 45 degrees, you only lose 1%. If you tilt it up to 60 degrees, you lose 7%. And you can see the different orientations here in different directions and what percent of maximum output you can get with that orientation. Okay, and I see a couple more questions came up. Fact of the matter is, even at north, you're at about 70% of the maximum output, depending on the tilt north. And that's a bit surprising. And in fact, the matter is that is cost justifiable now in terms of comparing the life cycle cost or levelized cost of energy for photovoltaics against the cost of the utility energy you're buying. So let's see what the next two questions are here. On elevator. Okay, oh, okay, Alaska presentation says 0.3%, downloaded document says 0.47. Okay, that's interesting. I don't know the answer to where that difference comes from, Greg. It could be the download. They are improving on the temperature performance of these modules. And it's possible that whatever was downloaded referenced an older module from back maybe 15 or 20 years ago, because the power now, this 0.36 refers to this modern 440 watt module we're looking at. Sherry is talking Alaska. And okay, Greg, this is a tough one. Which is it? Okay, I see. Which is it, 0.36 or 0.47? And I guess the answer is it all depends on the module itself. This 0.36 is for the one that we're using as the demonstration, but there are others where it can go up to 0.47. Okay, so this is just gives you a rough idea of what percentage you can get, even if you have this you know, if your module is tilted vertically in Alaska, you get a bigger percentage than you do if it's tilted vertically at the equator or in Florida. Florida vertical is just out of the question. You're down to about 53% or something. It's better to have it pointing north in Florida than be vertical. So, okay, let's see, got those, time to move on. So what are the options for good connected systems? Well, one is the straight grid connect. And when we come to a lot of words like this, I'm going to go through them relatively quickly, because what we're getting here is this is what is involved in the design of a system, is knowing these kinds of things. So I'm not going to go into detail on all these things, but we will come back to some of them as we go. So we have a straight grid connect, and the thing to realize with straight grid connect is that if the utility goes down, if it's lost, power pole or whatever, or a storm knocks some wires down, your PV system has to shut off. So it is not going to make electricity for you if you are disconnected from the grid, unless you have battery backup, because then your system automatically disconnects from the grid and makes electricity that's used only locally. Okay, now if the grid goes down completely, if the grid starts to fail, which happens sometimes in the afternoon if the grid is close to, or if the utility is close to the utility peak, then the last thing the utility wants is for the PV systems to shut off, because then it makes situations even worse. So the utility wants that PV in the afternoon because it helps them out. And there is now a special agreement possible with the utility as of 2020, according with IEEE 1547, the IEEE standard. It says that PV system owner, and generally it's going to be a large system, can sign a deal with the utility where the utility can take control of their system output and change the power factor and adjust the output to optimize the performance with the connection with the utility. But so in any case, the straight grid connects, you're able to sell back to the grid. The battery backup grid connect is just like the straight grid connect as far as the utility is concerned, but it has separate standby circuits powered by the solar and by the batteries when the grid is down. And the batteries are charged by the solar, but they can also be charged by the utility when the utility comes back up again. So what do you need for a properly designed and installed PV system? Well, you need, for sure, that it has to meet the electrical design performance specs. Okay, it better not leak if it's on a roof, and it's not unusual for 100 roof penetrations in an installation of a rooftop system. And the dealers, the folks who install these things, the only place the roof leaks is where it would have leaked anyway. The seals are extremely reliable. I mean, people don't like to talk about it, but if you get to know the people in the business, they don't want it to leak. I mean, that messes with their liability insurance. So they are going to do their best to make sure it doesn't leak, believe me. And out of thousands and thousands of penetrations, very, very, very small percentage of them actually leak. And they probably leak if they're on a roof that should have been replaced anyway. It better not blow away, because after all, if you want it to provide power for you after a heavy windstorm, it's got to stay on the roof. Now, when you figure these things are being bolted down to your trusses with 4-inch lag screws, your roof decking is certainly not anchored to the trusses with 4-inch lag screws. So fact of the matter is, your solar is going to hold your roof down better when it's bolted into the trusses. So it's always nice if it's aesthetically pleasing. And I can tell you when it's really aesthetically pleasing is if you've got battery backup and you've had a bad ice storm and you happen to have your refrigerator working and your coffee pot working, and your poor neighbor doesn't have any electricity. Refrigerator, probably, that's no big deal if it's cold outside, but it's nice to have the igniter and things working on a furnace. We like to say here in Florida that after a hurricane, the people with the battery backup systems are the envy of their neighbors, because they've got ice cold water and or they've got hot food and cold beer. So in any case, the other thing is the design has to last a long time. So it means you don't put cheap screws in these things. You use stainless steel hardware. and make sure nothing gets rusty and nothing falls apart. The mounting, for example, is high quality aluminum, and the screw is stainless steel. And contrary to some of the fears that were had by utilities 20 years ago about the interference with the grid of modern systems, when you've got IEEE 1547-2000 compliance, it means the grid the utility can control your system to have it enhance the performance of the utility. So those concerns have been mitigated, and PV is now the friend of the utility. The only problem is it competes with their revenue stream, but they're working on fair ways of taking care of that. So what do you need for a good system? Well, you need the modules. You need the racking to hold the modules. You need the mounting to mount the racking. You need an inverter or a bunch of inverters that are listed to UL 1741. There's some special provisions there. And the main thing is that UL 1741, which is the testing provision for IEEE standard 1547, is that the output of these inverters has to be at least as good a sine wave as the utility. Well, the utility is allowed 5% total harmonic distortion, which is the measure of the quality, and 0% means perfect sine wave. Most of the inverters on the market right now have less than 3% total harmonic distortion. So in fact, the output from an inverter is generally better than the utility output. So that's something you can do electronically very readily. Code compliant disconnects and wiring. And thank goodness we've got the National Electrical Code, and Article 705 goes into all kinds of descriptions of that, Article 690 and so forth. So between 690 and 705, you pretty much got all that taken care of. Some in Article 250 about grounding. You need a utility connection that the utility is happy with and the code is happy with. You need provisions to shut down this system rapidly if necessary, if the utility wants to see it go down. Hopefully you're going to need a permit for an inspection. And you'll probably have to sign an agreement with the utility that they will allow you to export electricity to their grid, and the most important part of what they will pay you for it. Most of the agreements, as long as you don't make more than electricity than you normally buy from the utility, is an arrangement called net metering, where they pay you the same as what you would pay them. And let me see here, these Q&A, did we leave off at 10? Yeah, we did. Okay. I don't want to miss any questions or answers, and I'm going to try to answer things, but sometimes my answer might be I'm not sure or I don't know. I hope you'll forgive me for that, but I do not know everything. And there are some very good questions. Okay. So this is a string-fed inverter system right here. All right, and this is a pretty straightforward system. You've got a bunch of, you notice that top row of 7 modules, and they're connected in series, plus to minus, all the way up. And then there's another row connected in series, plus to minus, and so forth. Now, these 2 rows then are connected in parallel at the inverters. The significance here is that anything connected in parallel will have the same voltage. So these 2 rows must have the same voltage. Anything connected in series should have the same current, and indeed they will have the same current, and they will adjust accordingly. So if one of these modules becomes shaded, it doesn't want to make as much electricity, and it's going to take down the entire array, because all of the rest of the modules has to adjust to the preference of that module. It's sort of like that one holdout vote, wherever it might be. And until that vote comes up, the whole system performance goes down. So that's a disadvantage here. The advantage is it's pretty straightforward and simple. the wiring, they're all snap connectors. You snap wire the modules together. You could have had a go out binging the night before and not mess up on how you wire the modules together. You might fall off the roof, but that's another story. So in any case, they're male and female connectors or plus and minus connectors on each of the modules, so that you can only connect a plus to a minus, not a plus to a plus. The junction box brings these strings down to the inverter. These are called either strings or source circuits. The inverter then combines them. It does maximum power point tracking on them. It looks for any ground faults. And it also does rapid shutdown. So there are mechanisms so that you can, if you turn off that inverter AC disconnect, it will shut the entire system off at the rooftop level and at the module level generally. The AC is generally connected into a distribution panel, and that's where the point of utility connection takes place. There are other ways to do it. We'll look at them later on. But this is a basic string-fed system. The one on the right is a microinverter system, and you'll notice that's a bit different. Every module has its very own microinverter. These microinverters, the most common ones are rated at about 290 watts, and they connect directly to the inverter, and they connect in parallel on the way out. Now, the significance here is that if you're going to connect sources in parallel, they have to be current sources, not sources of voltage, but sources of current. All of these are connected directly to the utility. So in other words, the output is 240 volts and the output is regulated by the utility itself. And furthermore, not only is it regulated the voltage, but the phase is regulated so that when the microinverter comes on and starts injecting current into the system, that current is injected exactly in phase with the voltage because the voltage acts as the synchronizing signal for the output of the microinverters. So each microinverter has its very own maximum power point tracking, and it has its very own rapid shutdown mechanism. So if the utility is lost, the microinverter shuts down and that's it. There is no more electricity leaving that microinverter, and it's perfectly safe to be up around the roof with all these modules. So you notice all these microinverters are in parallel, the strings are in parallel, all these current sources add, and so you've got 240 volts, and in the case of the more popular 290 volt microinverter, each one contributes 1.21 amps to the system. So if you got 20 of them, you got 24.2 amps. And 40 of them, you got twice that. Okay, there's an AC combiner and monitor, and that's each of those microinverters has its own communication link. So it talks to the combiner, and if it has a problem, it tells the combiner about it. The combiner makes an announcement. The owner finds out about it on the cell phone. The company finds out about it, and you can go and say, okay, inverter number 2, what's your problem? We're going to replace you or whatever. Warranty on the microinverters now is the same as the warranty on the modules, 25 years. So pretty robust piece of equipment. Okay, and they're living underneath the modules, so they're shaded from the sun, pretty much shaded from rain, a reasonably desirable environment. So this is a microinverter system. The advantage being that every module is independent of every other module. It does its thing, and they all contribute whatever they can to the overall current on the line. And here we have a DC optimizer. Oh, we have some more questions. Let's take a look at them before we talk about optimizers. Okay, which is it? Oh, wait a minute. Oh, we did answer that one. Let's see. Isn't it always live as long as the sun is shining? The module itself is live as long as the sun is shining. So up to the input connection to the microinverter, it's live. Okay, and there's nothing much you can do about that other than to put something over it to cover it. But you would have to touch the inverter leads in order to have any damage. The microinverter itself goes down. There is no AC output from the microinverter, and the microinverter is installed directly underneath the module. So I hope that is what you're asking about, Sheila. Let's see, Sobrato, which of the two configurations are more commonly installed? I can tell you of the some 1,400 installation I've worked on, about 90% of them are microinverters, and about 10% of them are optimizers, and about 0% of them now are straight grid connect. The straight grid connect is the way it's done with the huge systems where there's little possibility of shading, like that industrial system. So if we were doing utility scale, then we would not probably be using optimizers or microinverters. We just finished up 4 schools up in New Jersey in the 150 kilowatt range. All of them used optimizers. So we should be saying which of these 3 configurations are more commonly installed. And for residential, it's almost exclusively the microinverters and the optimizers, and partly because it is so convenient for the rapid shutdown requirement of the National Electrical Code. But the other part is the fact that these optimizers and these microinverters enable these modules to operate independently of each other. And in a residential case where shading is sometimes a problem from trees, whatever, it's very convenient not to have shading of one module affect the performance of another module. Okay, so let's see now. I believe that takes care of the questions. Very good questions, by the way. Whoops, here's a couple more. Does a combiner filter harmonics? No, the harmonics, the inverters themselves do their own filtering. So the output of the inverter is very, very clean. The combiner just combines the outputs because you got a bunch of like 5,000 watts or so at a time. And if you on 20,000 watts, you might have 4 of these strings in parallel. So that's what the combiner is. The combiner effectively is nothing more than a distribution panel running backwards, where the thin wires coming in are the sources and the fat wires coming out goes to the load. Whereas with the regular panel, the fat wires come in, it comes from the source, and the thin wires going out go to the loads, the stoves, the lights, the garbage disposals, and so on. So yeah, the filters have nothing to, the combiner has nothing to do with harmonics. As soon as that electricity comes out of the inverter, it is clean as a whistle. And so let's see, Don, what do we got here? Does each cell have internal protection and alarm monitoring? Each module. Modules have internal bypass diodes such that it partially mitigates a shading issue even with a single module. And there are other modules where they have half cells, which are effectively 2 modules in parallel in one enclosure. But the modules themselves are basically self-limited, as you notice on even if you short them out, it doesn't damage them. The current that comes out of them is limited. So the modules are mostly, if anything goes wrong with the modules, because it's being shaded. So I hope that is what you're asking. Rephrase it if I didn't do a reasonable job of addressing that. Okay, let's look at the optimizer system. Notice the optimizer system, that's a series connected system. You come out and start on the right-hand side, and the voltage starts getting bigger and bigger and bigger as it gets to the left-hand side. Now the optimizers, the 240 volt optimizers, will typically run at 400 volts. And so the inverter itself controls the optimizers. They talk to each other and amongst each other, and the inverter says, okay, guys, all of you on the top, I need you to work out a deal such that this total voltage from all of you is going to be 400, and whatever current you need to supply in order to get your voltage such that it'll make 400, that's what I'll take. But we're going to make sure that the voltage out of each string is 400. Now that means the strings don't have to be the same length, because the optimizers can cover for that. The string lengths can be somewhere typically between about 7 and 13, depending, even sometimes more, depending on the voltage of the inverter. And the inverter brings the voltage up. The current is then adjusted, but they're connected in series. And that's the difference. The control algorithm's obviously a bit more complicated here than it is when each microinverter just does its own thing and reports what it's doing to the monitoring system. But here with the optimizers, they all have to cooperate with each other in order to make sure the current is the same, or the current is the same in that series string, and they will adjust their voltages accordingly. And yet each one wants to be operating at its maximum power point. So a lot of different things going on here that have to be dealt with by the inverter. So let's, how are we doing on time? I hope we're not going over here. 2:53. Yeah, we need to move a little quicker, I think. A couple more questions though. Let's see what we can do. And by the way, those in the chat, I'm only looking at Q&A. I don't have time to be flipping back and forth here, or we'll be not getting through the material. How many wires are there between junction box and the inverter? Are there splices in the junction box? Yeah, the junction box, the wiring from module to module is open wiring with the special insulation called type PV insulation. And when you go to the junction box, the wiring it generally changes over to a different insulation type, and then the wiring goes in conduit down to the inverter. Now, the number of wires in that junction box will depend on how many strings there are. There will be 2 wires for each string plus 1 ground wire, equipment grounding conductor. So if you've got 4 strings, you'll have 8 wires and an equipment grounding conductor going down through that 1 conduit. So of course you've got to do, if you're electrical guy, Eric, you know that you have to derate your wires for conduit fill and temperature. So these are part of the design process, and we'll come to that a little bit later. Okay, but the number between junction box and inverter depend on the number of strings that are attached to the junction box. Typical inverter will accommodate up to 4 strings at the input. If it's in the, we're talking now about the optimizer type system as opposed to the microinverter string. But same thing with the microinverters, it's a matter of how many wires are between the junction box and the combiner box, where it combines the outputs of all of the microinverter strings into a single output that goes to the utility interconnection. Okay, so let's do some structural design here. Again, there are going to be a lot of numbers coming up here. And again, the whole idea is this is what one needs to do a proper job of mounting the modules and make sure they don't leak or they don't blow away. Okay, and so I wanted you to have the full picture here so that if you're really seriously interested in going in this direction, you'll be able to download the slides and get the and go over the material again. Okay. Design starts with the module, and they have to be listed. They've got the electrical properties, we know about that. They have thermal properties, we've already talked about them. They have structural properties. They can withstand a certain amount of pressure. Some can withstand more than others. Oftentimes the downward pressure they can withstand is more than the upward pressure they can withstand. So you need to know both, because the most serious wind loading on these modules is the uplift as opposed to the downward forces. I see there may be another question or two. I'm going to hold off for a minute and we'll go back to those. So the modules have to be strong enough, and it's nice if they get hit by falling branch or something, if they don't break. So they basically have not bulletproof glass, but you know, the same kind of glass you call hurricane glass that we have in our windows here, that can be hit by a 2x4 at a certain velocity and they crack, but they don't fall apart, or like the windshield on an automobile. So let's just do a quick example here. Let me see if those questions, what they are. Okay, just one. Is there a specific brand of system you have in mind when we refer to warranty standard connections, or is there in those? There's sort of a basic standard that, like the UL 1741 is a basic, you have to at least be this good. Other manufacturers take pride in being better than that. Certain manufacturers take pride in manufacturing a module that is adequate for use in the 175-mile-an-hour high velocity hurricane zone in South Florida, Miami area, for example, or out in the islands. So you can't build something that is less than the standard, but it's perfectly fine to do something that's better than the standard. All right, but there are the standards. There's standards for racking, there's standards for the structural thing, UL 1703 for the modules, 1741 for the inverters, lots of standards out there, and we're going to be mentioning them as we go. Okay, this particular module will withstand 113 pounds down and 75 pounds upward. And 75 pounds uplift will handle pretty much everywhere in Florida, depending on certain roof zones where there is more uplift pressure than in other roof zones. So you need to pay a careful attention to that. We'll take a look at that here in a minute. Maybe less than a minute. Okay, zone 1 is an interior, zone 2 is the end, 3 is a corner. And there's this quantity A, defined by the American Society of Civil Engineers and ASCE 716 by 10% of the lease. Lease for, that'll quit ringing in a minute. 10% of the least horizontal dimension, or 4/10 of the height, whichever is smaller, but not less than 4% of the least horizontal dimension, or 3 feet. Well, after you've read that 15 or 16 times, you have a pretty good feeling for what that means, okay? In any case, there's this definition of this boundary between zones, okay? And in ASCE 716, they finally recognized that solar is here to stay. So they have added a lot of good stuff in terms of calculating wind load on solar modules that you had to guess on in previous versions, the ASCE 710 and so forth. So when you're going to fit them on the roof, you'll generally draw the roof and you'll get all those dimensions down and you'll define the zones. And here we show that little number A, and we got zone 1, which is the center, which has the least pressure. Zone 2E is not quite as much pressure. Zone 3 is generally a lot of pressure. Zone 2R is more pressure in this kind of a hip roof configuration. But all these numbers are there for the asking in the ASCE publication, ASCE 716. If you're designing solar, you need to have 2 handbooks either on your computer or on your desk. And one is the ASCE 716. The other one is the most recent version, or whatever version of the National Electrical Code that's being used in your jurisdiction. All right, so you draw your zone and then you add the modules. And you notice that some of the modules overlaps the zones. And what's fun here is you can do average pressure on the modules by calculating the amount of area in each zone times the amount of pressure in each zone divided by the total area of the module. And that gives you the average pressure on the module, and that has to be less than the allowed pressure by the manufacturer. Okay, so here we've got an array. Generally, you stay away from the edges. You want to generally stay on the bottom edge. For example, you want to stay 10 inches away if you can, because there's a penalty if you get closer. The wind tends to lift up underneath that, and the wind pressure is significantly more. So when you see modules are on a roof where they're overhanging the top or the bottom, the design Well, they will stay there until a nasty wind comes along, and then there's a little bit of chance that there will be a problem. I'm going to take a quick look at the chat and see what's happening here. In general, I don't know what you're getting from the professor. I don't have an answer. Okay, you're going to get them replaced. Okay, with the newer set. It must have been accidentally loaded differently. Yeah, no, the slides that you will get will be this presentation that we're doing now. All right, I think that's the essence of the conversation in chat. Okay, that's it for Q&A. Okay, so we got our modules mounted. Now what? Well, we determine the wind load. And what do you need to know to do that? How high is the roof? What zone are you in? You saw evident indications of what the zones there were on that last slide. You need to know the risk category. We're going to talk about that on the next slide. Exposure category. This is, are you in the middle of an open field, or do you have trees and other houses around you? There are 3 exposure categories: escarpments, that means hills, size of the module, anything smaller than 20 square feet, there's more pressure on that than if you exceed 20 square feet. The slope of the roof makes a difference. The speed of the wind, of course, makes a big difference. The pressure is proportional to the square of the wind speed. So that means that 141 mile an hour wind has twice as much wind pressure as 100 mile an hour wind. Okay, so that's what you need to know. And once you know these answers, you plug them into a formula. What's a risk category? Well, risk category 1 is structure with low risk to human life. Category 2 is everything that isn't specified in 1, 3, or 4. That's the good way to make sure that you're talking about everything. And category houses fit in category 2. Category 3, if they can pose a substantial risk to human life, economic impact, such as release of toxic or explosive substances. And then there are the places that the storm center care, emergency service, and so forth. That's category 4. So you need to know the risk category of where you're going to put the arrays. ASCE tells you exactly how to calculate the wind load. Each risk category has its own wind speed contours. The higher the risk category, the higher the design wind speed. Simply means that you design it stronger. Even though the wind maybe doesn't blow as hard, you want to make sure that it's going to hold up at where the wind is going to blow. Because after all, if you're in a 170 mile an hour wind zone, maybe once every 1,000 years, the wind blows 175 miles an hour. So, or so whatever number of years. Okay, so you get the design wind speed, and then you have to calculate this quantity QZ. And the 0.00256 represents the density of air, because if the air had no mass, then there would be no pressure to worry about. And then you got a bunch of coefficients, okay? And you have to figure out what they are. V squared, of course, is the velocity of the wind. And so we mentioned the square of the velocity. Again, these formulas, I'm just showing you these because these are things you need to know if you're going to do the job right in designing these systems. And at least somebody needs to know these on the team. All right. So we're going to describe what these coefficients are. QH and QZ. QZ is just the wind pressure at a certain height, and QZ depends on the height above ground, and that depends on the KZ. And the QH is evaluating QZ at the mean roof height of the structure, okay? The others depend on roof height, roof zone, module size, roof slope, topography, building shape, elevation, lots of other stuff. That there are lots of pictures in the ASCE 716 that tell you what all these things are. So how do you determine KZ for heights up to 60 feet? You look it up on the table. If you are in exposure B, anywhere from 0 to 15 feet, in fact, anywhere up to 30 feet, your coefficient KZ or your coefficient KZ is 0.7. But exposure C, which is a more open area, the wind can whip up stronger in exposure C. So your coefficients are larger and your corresponding wind pressure is going to be higher. Exposure D is like being right next to the ocean. You got a mile, at least a mile of open space, or you've got 5 or so 100 feet of some trees, but then you got another mile of open space, big lake, big ocean, whatever. And that's where these coefficients get pretty big, like 1.831 instead of 0.85 at 60 feet above ground. The ASCE 7 gives this height all the way up to, I think, 160 feet. So, and ways of calculating it for even higher. The higher you go, as you can see, the harder the wind blows. So that's the KZ. Here's our exposure categories. B is sheltered. C is every place where B or D don't apply. And D is basically unsheltered. And so in between the unsheltered and the sheltered is the C cases, okay? And for example, C is a little more stringent than B, and the two South Florida counties, Miami-Dade and Broward County, both require all wind load calculations to use exposure C, regardless of whether formally it would be a exposure B. So there's check with your jurisdiction on these requirements. So what about these other coefficients in ASCE 716? Okay, well, the GCP are the exposure coefficients, and they depend on the roof slope, system exposure, and the roof zone. The one we're looking at right now is a hip roof that has slope between 7 and 20 degrees, and it's in exposure B. Okay, but it could have been something else. We could have done a different example. The whole idea here is this is a process you go through after you identify these various things. And this is interesting because you've got your downward and your upward forces. The uplift forces have minus signs and the downward forces have plus signs. Notice that in general, the lift is more than twice the downward force. Okay, and the big time loser here is zone 2R. That's along the edge of the roof on the top. You have to multiply by minus 2.1, that long formula for the GCP. Okay, in other words, the exposure coefficient. If the terrain is flat, then KZT, that's the terrain coefficient, that's equal to 1. But if the structure is a house, like a normal thing, KD is 0.85. Okay, and altitude less than 1,000 feet, case of E, that relates to the density of the air, and it gets lower as you go higher where the density is lower. So you're going to pay very careful attention if you're in Denver at a mile high. But anything below 1,000 feet or so, case of E is sensible to use just 1. But if you're at an altitude above 1,000 feet, you'll want to look at ASCE 7 and find the correct value of KE for your formula. If the slope is greater than 7 degrees, then this gamma is relates to the area of a module. So gamma sub A is 0.7. And again, these are lookups in chapters mostly 26 and 31. I can't remember the exact chapters. In any case, if you have 115 mile-an-hour wind speed, and I use that because that's pretty typical in the Northeast, then your QH times gamma E times gamma A is about 14.1 pounds per square foot. All right, so we can make a final wind load determination then by multiplying the 14.1 pounds per square foot by the GCPs, and you see what you're in the various roof zones then. The pressure ranges from, and notice in every zone, the downward pressure is the same, 8.46 pounds per square foot. But the lift is more in certain zones than in others. 2R being the most at 29.6. Now these lifts can easily approach 75 PSF on certain roof zones in the South Florida area. And those are the kinds of designs that my group typically is working with. So we're pretty fussy about making sure these arrays are held down. So now we can figure the overall forces on the modules because we know what these pressures are in each zone. Okay. And so we propose a mounting system, and it's generally a good idea to try to make sure you've got mounting rails that are mounted on alternate trusses as whenever possible, so that you don't put all the load on one truss and no load on any other truss. So, and also when you get into high pressure zones, you tend to want to have more mounting points than in the lower pressure zones in the middle. So what we're looking at here, the brown things are the attachment points, and the blue things are the mounting rails. Okay, and so what are the forces on the attachment points? Well, if we look at each row, there's 54.9 square feet in zone 1, 35.1 in zone 2R, and that characterizes the top row. So the total uplift on the top row is 2,046 pounds. In the middle row, the total uplift is 2741, and on the bottom row, the total uplift is 4,066. Now, of course, there's more modules in the middle and on the bottom, so there's also probably going to be more anchor points. So in any case, if we look at the mounting points then on each row, you got 11 mounting points on the top one, so each one has to hold 186 pounds, 17 in the middle, so that's 161 pounds each, and 21 on the bottom, so each one then has to withstand 194 pounds uplift. And this almost sounds like fun, doesn't it, folks? I mean, everybody likes to do multiplication and division. That's what we're doing here, and looking stuff up in tables. So we got all these average forces on modules now, and we now know what the average uplift on the mounting points is, so we know how far the screws have to go into the wood in order to not pull out. And we can find that out by normally what the wood that's used for trusses where you live is going to be based on the wind speed. And here in Florida, we generally use yellow pine because yellow pine is fairly dense wood and it has a fairly decent withdrawal strength. And so here's some numbers. Yellow pine, a 1/4 inch screw. If you screw it in by 1 inch, you got 281s with a 281 pounds allowed per inch with a safety factor of 4. 5/16, 332 pounds per inch. And you know, safety factor of 4 is arbitrary. A safety factor of 2 is actually pretty good. So that would be 664 pounds allowed in southern yellow pine for 1 inch of penetration into the truss. And Douglas fir, the number goes down, but the Douglas fir wouldn't be used for a truss in a high wind area, more than likely. Okay, so we got the design built now so that that's not going to blow away. Let's look at the electrical outputs here. Let's look at the time here. 3:16, we got 45 minutes going. Okay, let's see if we can make it. Let's do we're going to do several electrical design examples for this very same array. Oops, here's let's see what we got. Oh, I did answer that already. Oh, here's number 18, sorry. Two more. Have I worked on installing panels on existing roofs where you cannot penetrate the roof membrane? Risk of losing warranty. Okay, there are certain roof membranes. I wonder if you're talking about the kind like on a flat roof. We, on residential roofs, there, we have about out of thousands of systems, basically, that's not an issue. There are arrangements between the manufacturers of various mounting hardware and roofers so that they've gotten lots of approvals. And but I think I know the type of roof. And generally, in cases there, you go straight to the manufacturer and say, what do we need to do to make sure that your roof is going to be happy with our system? Did a system like that on the roof, a 1 megawatt system on the roof of the Orange County Convention Center about 13, 14 years ago. And we had to work very closely with the manufacturers of that membrane. So the answer is mostly no, but on a big building, and if you have one of those membranes that you're not even supposed to walk on, then you got to be careful. Let's see, overall panel weight and downward pressure to see if the roof can structurally handle the extra load. Yeah, we do that too. And the typical downward additional pounds per square foot downward pressure is about 2.6. And if the roof can't handle 2.6, then it can't handle somebody walking on it. So good points, Vibrato. We yeah, that's I point out that it's the upward lift that's the critical one. But if you got it screwed down, and then you need to clearly observe that you can take that extra weight. So the answer is about 2.6. The most I've seen is about 3.1. And most roofs, if you walk on the roof, it'll only support 3.1. You're going to want to get off that roof because it's going to feel like it's going to collapse under you. Okay, good questions. Very good questions today, folks. I commend you for really good questions. All right, let's look at some electrical designs here. We're going to do a microinverter system, an optimizer system, a string inverter system with 3 of them. And every one of these incorporates maximum power point tracking, and they also incorporate rapid shutdown at the module level. All right, because this is what's now required by the latest National Electrical Code. And rapid shutdown means that when you flip a switch, the entire PV system shuts down outside the boundaries of the array. So if you walk alongside of it, there is nothing live. Okay, here's the details on inverters for this UL 1741 we've been talking about. They have to have good waveforms. We talked about that. They have to disconnect if the utility is either over or under voltage, over or under frequency, unless there is a special arrangement with the utility. Anti-islanding is very important. Imagine if your inverter thought my inverter was utility, so therefore my inverter kept your inverter working. The reason that doesn't happen, and the reason that you can have multiple inverters connected to the utility, and every single one will shut off when the utility goes down, is because they are being synchronized by the utility voltage. And the waveform of the reason that the inverter output waveform is not perfect is because it has a little glitch when it goes through 0. And that's the synchronizing glitch. And if there is nothing to synchronize it, the inverters are programmed such that the current frequency drifts away from 0 or the 60 hertz. And when that frequency drifts away, and within about 2 seconds, the inverter realizes that there's nothing there to synchronize the signal, and it shuts down. So this is a very important concern here, and then utilities have had a lot of concern about it. And but there's so many experiments have happened now over the years that it's well documented that the anti-islanding requirement works so well because the inverters act as current sources that are necessarily synchronized by the utility voltage, which if it's lost, they lose their synchronization and they go off frequency and they quit. Okay, now IEEE 1547-2000, as we mentioned earlier, offers utility the option to help control your array. It can control the power factor to help reduce losses on the utility line. All sorts of interesting things they can do now to help your PV system to help them. So let's look at a microinverter system design. We looked at this before. What are we going to do? Well, here's the rules right here, and I'm going to go through them rather quickly, but if you want to design a microinverter system, you'll want to read these more slowly again, and then you want to get some data sheets for all the microinverters and all this kind of equipment here. Because the data sheets are usually 2 pages long and you give you lots of good information on the microinverter. They're different from the installation manual, but if somebody also at some point needs to read the installation manual. But in any case, you have to match the microinverter to the module. And usually that means that the number of cells in the module, including the open circuit voltage and short circuit current, needs to match up with the input characteristics of the microinverter. Some microinverters are designed for 60 cell modules. 60 cell module generally has a working voltage of around 32 volts, and its voltage might go up to somewhere 38, 39 volts in open circuit. Most of the microinverters now, though, are perfectly happy to handle higher power 60 cell modules or even a 72 cell module. And again, when you see the number of cells, that generally indicates multiply the number of cells by 0.5, and that gives you about the voltage you're going to get when it's operating. Multiply it by about 0.6, and that's going to be about your open circuit voltage for the module. So if you got 72 times 0.6, you're looking at an open circuit voltage in the mid 40s somewhere, maybe in the high 40s. Okay. The rated microinverter output current determines the maximum number of modules per circuit, because normally the circuits are only allowed 20 amps. That is 20 amps of overcurrent protection, which means your current in the circuit can't exceed 16 amps. So with the common microinverter output ratings of 1 amp, 1.21 amps, 1.45 amps at 240 volts, you can have 16 of the 1 amp inverters, 13 of the 1.21s and 11 of the 1.45s, and not go over 16 amps. Let me verify that 1.45. I haven't done any of those for a while. 16 divided by 1.45. Yeah, 11. You can have 11 of those. So it's 11, 13, and 16 on a single circuit. And if you have more than that, then you have to add additional circuits. You can have as many microinverters as you want, up to the maximum number. One of them on a circuit is okay. There's no minimum number, just a maximum. Modules rarely generate rated power, so the microinverters can handle modules with power ratings up to 150% of the microinverter rating. And if you do a simulation, it's very interesting. I'll go and show you a picture of that a little bit later of why it's okay to do that. So a 290 watt microinverter can be used with 60 or 72 modules rated up to 440 watts. And that's right on the spec sheet for the microinverter. So this is your circuit diagram. Here's the rules. That's it. Just that simple. You've got PV combiner for the microinverters, and the manufacturer generally makes a box that does that for you as long as you have 4 circuits or fewer. Otherwise, you put their data acquisition unit. You use the larger combiner box from a different manufacturer, and you can still use the monitoring unit along with the larger box, so that you still monitor performance of every single microinverter in the array. Okay, let's see now. I think we stopped at 18 questions here. I want to make sure we got it done. Yep, we're good so far on questions. Okay, so this is pretty straightforward, and this is probably why almost 90% of the designs we do are microinverter systems. How do you match the module to the microinverter? Here's a 400 watt module, the characteristics, okay? I gave a hint here before, but here's some numbers for you to look over later on today if you download the slides. And again, a typical 400 watt module is a 72 cell module. as they're basically measure about 1 meter by 2 meters in dimensions. Open circuit voltage 49.8, short circuit current 10.36, maximum power voltage 41.7. You can read those numbers. The important thing is that when it's really cold, that open circuit voltage will go up to 56 volts, and when it's really hot, that maximum power voltage will drop down to 35.5 from the 41.7. So you need to make sure that your microinverter will cover that range of operating voltages. And the module can be used in a system up to 1500 volts. Okay, not all modules are rated for 1500 volt systems. So if you're building a 1500 volt system, which you're not going to do for a residential install, you can still use this module in any system up to 1500, but 1500 volt system is going to be behind a fence someplace. 290 watt microinverter, what's the characteristics here? Well, here's what we got. Maximum DC input voltage in yellow. Let's find yellow ones. Okay, see, even when it's cold outside, the maximum output voltage of the module does not exceed 56, so we're good on the yellow one. The orange one, maximum power point tracking range, is it'll track the maximum power voltage from 27 to 45. And sure enough, we're going between 35.5 and 41.7. So we're good on that. Maximum module short circuit current, 15 amps. Well, module short circuit current is only 10.36, so we're well below that allowed value. The maximum output power of the microinverter is 290 watts. So if for some strange case, this 400 watt module, we're trying to crank out 350 watts, the microinverter will only use 290 of it. Actually, probably about 295 because there's slight inefficiency in the microinverter. But the microinverter simply shifts the maximum power point tracking a little off peak, so they only take the maximum amount of power they can use from the module. And again, I'm going to draw you a picture, show you a picture of that in a little while. Output voltage of 240. So so any modules in the power range from 235 to 440 are perfectly happy with that microinverter. And so the 400 watt module, the microinverter, is perfectly happy with that. Efficiency of 97%, that's not half bad, converting 97% of the electricity at the input to useful AC power at the output. And the DC input from the module, neither one of the two leads from the module into the microinverter are grounded. Okay, that's an important thing. That's why the microinverters are transformerless and so light and so efficient, because it's an ungrounded array. That's been going on for a while now, and people were nervous for a while, but they realized this is a very good way of making electricity. So you select your components. Let's say we got that 400 watt module on that microinverter. We got 20 amp circuits, so we can only have 13 per circuit. So here's our array up on the roof. How might we configure that? Well, we could do 2 circuits of 12. There's 24 modules there. And we could, there's one circuit with 12. And we can start filling the rest of these, cooking them up. And sure enough, here we got another circuit of 12. So we got 24 modules, 2 circuits of 12. We could have had, if we wanted to, 1 circuit of 13 and 1 circuit of 11. If we took that number 1 module that's in the second row and just turned that into a 2, we could have had a 13 and an 11, and we still would have been within the design guidelines. So that's up to the person doing the wiring. If they think it's easier to do it the other way, then they can do that. Performance of the system does not measurably change by doing that. Each circuit has 14.52 amps. That's within the allowed 16 limit. The array itself is rated at 9600 watts DC. The total AC rating though is 24 times 290. And what is 24 times 290? I better multiply that out. And 290 is 6,960. And most of the time, the array is going to be operating at less than 6,960 anyway. And what counts on this is the annual kilowatt hour production. That's what we're designing for, is the annual kilowatt hour production. And the more kilowatts we put up there, the more kilowatt hours we're going to make, even if we just use the same 290 watt inverter. All right. The microinverter cabling is provided by the manufacturer, and the circuits are fed to the combiner box at ground level. We showed that in the diagram. And so here we go. There's what are we going to do when we get down to the roof? There's a combiner box. And oftentimes after that combiner box, we now have just two wires coming out, 240 volts worth. Okay. And I show neutral, but this is a single line diagram. So that black line actually represents two wires. But we show the neutral and the ground separately. And so we go to the point of utility connection. So we come down from the roof with two circuits, two 20 amp circuits, combine them, go to a disconnect, and then we connect to the utility. And let's look at some of the ways to do that. Okay, here's one way. Feeding a circuit breaker, backfeeding a circuit breaker at the bottom of the bus bar of the main distribution panel. And 125% of the PV current in this particular case, there's 24 modules, 1.21 amps each, and 125% of that is 36.3 amps. So we need a 40 amp circuit breaker for that. Now, there's a rule here that says that if you feed opposite the utility on a bus bar, that the sum total of the main breaker plus the PV breaker has to be less than 120%, sorry, 125% of the, 120% of the bus bar rating. All this cold weather down here in Florida causing my throat to be scratchy. So notice we got 240 amps here between the 200 amp main breaker up there by the meter and 40 amps from the utility, and 120% of 200 amps happens to be 240 amps. So we meet the so-called 120% rule for backfeeding that 200 amp bus bar. Well, does that mean there's 240 amps on the bus bar? And the answer is no, because at 40 amps from the bottom, if you have a calculated load on this bus bar of 150 amps, that 40 amps is going to take care of 40 of them at the bottom, the first ones it comes to as it goes up towards the utility, which means that's 40 amps that the utility does not have to provide. So it actually reduces the load on the top of the bus bar by feeding it from the bottom there. All right, so this is one way to connect to the utility. All right, check the time, Roger. 335, okay, we're doing. All right, this is your code reference, okay. 70512B23B, one of our favorites. And that's just simply the 120% rule. Okay, now sometimes, since 236.3 is less than 240, we're good. Okay. Now I said 40 amps, but really, technically speaking, we have to use the 36.3 amps for the calculation. So it's 200 plus 36.3, and that's less than 240. But also 200 plus 40 is less than or equal to 240. So normally it doesn't really make a difference. It only makes a difference when you're getting up over 60 amps. And sometimes using just 125% of the inverter current will allow you to use a smaller wire. All right, so let's look at some other options here. AC circuits from PV are 240 volts. We already noted that. All right, now what if the 120% rule doesn't work? In other words, maybe that distribution panel might be completely full of circuit breakers and there's no way that you can double up on any or put in tandems or do anything else. You got to figure another way to do it. Well, all right, here's what's coming down from the roof, and what you might try is one thing is if the solar plus the main circuit breaker exceeds 120% of the bus bar, or if there's no room, then you can do this. You can do what's called a line side tap. Now, sometimes you can do this, sometimes you can't, because sometimes that 150 amp breaker is connected directly to the utility meter by way of a bus bar, which does not allow for any connections between the main circuit breaker and utility meter. But if you've got wires between the main breaker and utility, then you can do anything up to 150 amps tapping in on the utility side of that 150 amp breaker. But notice you're on the customer side of the meter. So the customer is still getting credit for that PV, and that PV current is still going to be the first thing that 150 amp breaker uses for the loads in the occupancy. And anything the PV doesn't supply then is going to be supplied by the utility. All right. So that's another way that sometimes you have to do it this way. And then again, if you can't get to the line side of that main breaker for reasons like I mentioned, then you might want to try another way. There's the load side tap. This is 705.12b22. And that looks like this. You add an extra 150 amp breaker at the top of that panel. You got 150 amp main, you can't get on the line side, so you tap on the load side. And as long as there are no other loads between the 250 amp, between the two breakers, the two main breakers, then the current from the PV will either go down to the loads below it, or if the loads below it don't want it, then it goes up the line. But in no cases do those feeder cables between those 250 amp breakers have to handle more than 150 amps. So this is another tie-in. It's called a Hawaiian tie-in. And I tell you, we use this relatively often because there's many cases where you just can't do the other two possibilities. This is a third choice. Okay, so I just wanted for sure needed to make sure everybody knows about these, because this is something not everybody necessarily knows about. So this is one of the secrets that you're welcome to share now that you know these three secrets here. And now we say that no other loads may be connected between the two 150 amp circuit breakers. Well, yes and no. There are some provisions for an engineered calculation to prove that you'll never exceed the rating of that feeder between the 250 amp breakers by adding extra loads. And as long as that doesn't happen, then that's okay too. But we're not going to go get that complicated. These three cases that I've mentioned cover 98% of all of the interconnects. So almost never do you need to worry about anything else. All right, here's an optimizer system. Let's design one of those. Let's look at the time. 3:40. Still Q&A at 18, so we can move on with the optimizer. What's different now about designing one of these? Well, we have to know about the optimizers. They are DC to DC converters. Like I might have 40 volts and 10 amps at the input, and that would be 400 amps or 400 watts. So that means I need 400 watts at the output, but I can get that with different combinations of current and voltage, and that's what the DC to DC converter does. The DC to DC converter is like a transformer. It will transform the DC voltage up or down, but the power in has to equal power out. So if the DC voltage goes up at the output, then the current has to go down at the output, so that the product of current times voltage at the input is the same as at the output. Now there's a 1% loss on these optimizers, which is amazingly low. So it's for analysis purposes, you just need to acknowledge that the input power equals the output power. But the output power is conveniently adjusted so that all of the optimizers can run at the same current, and the sum total of the voltages adds up to 400 volts for the optimizers. The optimizers do maximum power point tracking on an individual basis. So if you shade one module, that's okay, it adjusts to that. I mean, you lose power, but at least it doesn't affect other modules. They balance the outputs of each modulator, each string. They do rapid shutdown. They're controlled by the main inverter. So you can't use any old inverter along with the optimizers. It has to be by the same manufacturer, designed to talk to each other. Some manufacturers will be probably signing various agreements that you can use my inverter with your optimizer or vice versa. But if you want to be safe, it's a pretty good idea at this point that you're going to use one product as an optimizer. If you choose a particular inverter, it's better to choose the optimizer of the same manufacturer. Number 7 could be confusing, but what all it's saying is in each of the strings, the optimizers have to have the same output current, but they can have different output voltages. If the sunlight intensity on each of the modules is exactly the same, then each of the modules will have exactly the same output voltage as well. But if there's any variation in the performance on the module, it will be accounted for by the optimizer. Okay, so here's your design rules now that we know all about the optimizers. They have to be matched to the module current and voltage. Circuits may have different numbers of modules, but there's a minimum and a maximum length depending on the inverter itself. Oops, guess who spelled inverter wrong? I will take full responsibility for that. The total array power should not exceed 155% of the inverter rating. Okay, that's what the inverter manufacturer says. So if I've got a 100-watt array, if I have a 155-watt array, which is not practical, let's say 15,500 array, I can handle that with a 10,000-watt inverter. And again, we're going to see a picture of why that's okay in just a minute. Okay, but anyway, here's your design rules, pretty straightforward. The systems work well. One of my colleague engineers has one on her house, and it's been working just fine. He's got a 7,600-watt inverter and about, I think, around 10,000 watts of modules. And they make a lot of their own electricity. Matching the module to the optimizer, same exercise as matching the module to a microinverter. But here's our 400-watt module again, and looks at a suitable optimizer has to handle all these extremes of the module. So let's look what a suitable optimizer does. Rated DC input power of 400 watts. Okay, that matches to a 400-watt module. Absolute maximum input voltage is 60. Input voltage, that would be the open circuit voltage at minus 20 degrees C, the yellow one there. And that's 56, so that's okay. Maximum power point tracking operating range 8 to 60 volts. Well, that's certainly fits 41.7 to 35.5. The maximum module short circuit current 11.75. And the module short circuit current max is 10.36, so we're good there. Weighted efficiency of the optimizer, 98.8%, 1.2% loss, not too bad. Maximum optimizer output current is 15 amps. So if the array wants it to go to more than 15 amps, the inverter is not necessarily required to run at 400 volts. That's the nominal operating voltage, but it can raise that a bit if it's necessary to reduce some of the currents. And the maximum optimizer output voltage is 60. So that tells you if you want to run at 400 volts, you're going to have to get 60 volts from, you can't get more than 60 from each optimizer. So 400 divided by 60 is 6.666. So therefore, you have to have at least 7 modules in your string. Otherwise, you can't get up to 400 volts with these particular optimizers. Okay, so reasonable match. And this is where the design comes, is matching the optimizer. And then the optimizer just connects into the, then you match the array to the modules such that you don't have more than 155% of the inverter rating in your array. And as long as you match these, you're good to go. So what about inverters and circuit lengths? Well, array plus optimizer, the array is 9,600 watts. So the optimizer, we have to figure out some circuits here now, okay? So 15 amps, so that's 26.7 volts if there's 15 amps out, and if we split that into two groups of 12. So here's the results here. So 24 modules, if you have 2 circuits of 12, and a 7,600 watt inverter with 400 watts or volts and 15 amps max. That's kind of what you're looking at for the array plus optimizers. So either one of the circuits, the maximum power is going to be 6,000 watts. And the maximum power in each of these 12 times 400 is 4,800. So therefore, each of the circuits is well within the allowed power. So here's your inverter. No more than 11,800 watts in. We're meeting that. We got 9,600, so the yellow matches. Maximum input voltage 480. See, okay, so that means it can adjust up to 480 if it wants to. It likes to do 400, but it can go up to 480 if necessary. And that's the inverter's decision to optimize the performance of the system. No more than 20 amps input though. So 20 amps times 480, that would be 9,600 watts, wouldn't it? So that's 7,600 watt inverter. So you're not going to have 20 amps in and 480 volts in at the same time. Okay, you're not going to ever have more than 7,600 watts in. Output voltage 240, output current maximum 32 amps. So you need a 40 amp circuit breaker because 125% of 32 is 40. Beautiful inverter, 99% weighted in efficiency. Ungrounded input, same thing, same reason. Ungrounded input allows for it to operate more efficiently. And that's where you get your 99% efficiency. Almost nothing operates, even a water heater hardly operates with 99% efficiency when all the heat is generated right inside where the water is. So let's observe some more things. Modules and optimizers operate independently. So therefore, the modules can be oriented looking in different directions. That can be shaded. Some can be pointing south, some can be pointing east or west. Can't do that with the straight string. But since they can operate independently of each other, they don't all need to get the same amount of sunlight. Here's our minimum of 7 modules. Circuit length needs to be generally less than 15. So anything between 7 and 15 is okay. You can have 15 in one and 7 in another and 12 in another, and the inverter should be able to handle that. Okay. Determine your circuits. Let's set them up here. 2 circuits of 13 plus 11 this time. So here's our third, what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I guess we're going to have 13 up on top. And this is just about how fast the guys wire them when they're up on the roof, by the way. They don't waste any time. 400 volts per circuit, 9600 array, optimizer cable provided by manufacturer listing. And the circuits feed the inverter at the ground level, just like we just looked at with the microinverter circuit. So here's our ground level, same thing, except now we have an inverter rather than a combiner, but it does combine the DC output from the optimizers on the roof in 320 amp circuits, okay. They're not going to have 20 amps on those circuits, but they're 20 amp circuit breakers, okay. And you might have this connection, which is the 120% rule. You can do the other 100% rule, or I mean, you can do the line side tap, or you can do the Hawaiian tie-in or the load side tap, whatever you want to call it. So the same rules apply for the utility connection, regardless of what's on the roof. Now, here's what I was promising you about the DC to AC ratio. See, if you simulate the system, let's say that you've got a microinverter that's rated at 290 watts, and we connect to it a DC to AC ratio of all the way up to past 1.5. And what we want to see is presumably the annual kilowatt hour output will be linearly dependent on the amount of DC power. And yet one wonders, how can that possibly happen when the DC power is so much more than the AC power? Well, the answer is the DC power may be the rated power, but the actual DC power, like at 3 in the afternoon when the sun is only shining down at 600 watts per square meter, it's not going to be anywhere near the rated power. So what we have here is different modules connected. And this is based on a simulation with the National Renewable Energy Labs, SAM. And it's in Orlando with module facing south with an 18-degree tilt. Let's see, that's a 412 roof, no shading. And here's what you get. All the way up from 300 watts to 440 watts modules, you get a linear increase in output power. So when we say, and when the manufacturer says, you can put 150% more DC on my inverter than my AC rating, and I will still make you happy and convert all of the available sunlight into electricity, it is pretty much true. The loss up there near the 1.5 range is about 1%. So the whole idea is that don't be afraid when they say that. The simulation shows you can simulate for 8,760 hours out of the year. And it shows you where you have more sunlight than you're allowed. Time? 3:55, a few minutes to go. Okay, so without microinverters, I'm just going to click this one quickly. And again, if you wanted to design without microinverters or optimizers, then you have to go through this exercise here, okay? And you actually have to calculate the maximum and minimum array output voltages, okay? Because they have to match the inverter maximum input voltage and the inverter minimum maximum power point tracking voltage, okay? So again, here you can read this. We're running a little short, so I'll make sure we get there. And you just want to calculate total array power at standard test conditions to make sure the inverter is about the right size. And if you've got a DC to AC ratio of about 1.3, that's very comfortable. Pick a module. Okay, and again, this is just the math that you go through. So again, I'm just going to show you, this is how you do it. but we're not going to look at the numbers specifically and carefully, because if you want to go through this exercise again, you can order the slides and go through them at your leisure. I wouldn't want you to skip your favorite TV show or anything, but who knows, whenever you might have a spare minute, have a look. It's not unusual to have a hottest temperature of 65 degrees, even in New York or New England or Minnesota. When it is 100 degrees Fahrenheit outside, 65 C is not an unreasonable value for the temperature of the module, because after all, you've all walked on hot black asphalt and or even beach sand, and it's a whole lot hotter than ambient because it sucks up that energy from the sun and it converts it to heat. And that's what these nice black PV modules do. They convert 20% to electricity. They reflect some of it away, and about 75% of it gets converted into heat. So, of course, then half of that heat radiates upward, half radiates downward. So what does that mean for the amount of sunlight hitting your roof? Less than half as much, maybe about 40% of what would otherwise hit it if the sun were shining directly on the roof rather than on your solar system. So guess what that does to the lifetime of your roof? It doesn't dry out as fast, it lasts longer. Another one of those hidden benefits, okay? Need at least 7 modules to reach 245 volts. 8 would even be better. I went 7.02. So in any case, easy to go through this and see what you got to do for if you don't have the microinverters. But like I say, this is normally reserved for the very large systems where there are no issues with shading or changes in performance of modules. And that's the end of it. I like to talk about who these people are. The young man on the right is going to finish his electrical engineering degree next spring. The young lady on his left is his sister. No, the young lady is on his right, actually. That's his sister, and she gave birth to my first great grandchild last July. So that's why they will appreciate it, because if we take good care of the planet, my children, grandchildren, great grandchildren, and yours will be very thoughtful. So there's question number 19. Let's take a look at what the new one is here. Got that one, but there's another one here. Oh, Randy says, thanks. Randy, you're very welcome. I hope that you benefited from these 2 hours. I can tell you that my company is only a year old. Not that everybody in the company, a couple of us have had a whole lot more experience than that, but as a company, we're a year old. We are looking for people all the time. We're looking for good engineers. We are looking for site surveyors. We are looking for draftsmen and so on and so forth, even business managers. So, and we're not the only guys out here hiring. There's a lot of work to be done in the PV area. And I'm hoping that as you get involved, there will be more and more and more engineers. Our philosophy is very simple: train the competition to make sure they do it right. Because if they do it right, then we all benefit. There's plenty of roofs out there for all of us. So let's all get involved and do the job right. And again, if you want to go through the slides again, be sure to order them up and feel free to share them. The whole purpose here is, from my standpoint, is for as many people to learn this material well as possible so that we all get it right. Any other questions? I'm looking at my Q's and A's here. And I see a few more chats up there. What do we got there? The test questions, I believe they are based on the current presentation. Because when the original presentation was done, the quizzes weren't required, I don't think. So, and if that's not the case, I've got current test questions. and I'm sure that it'll work out so that you'll pass the test. I just wanted to put a little more emphasis on the modern systems. The material in the previous one covered these kinds of things, but not to the extent that I felt was worthwhile at this point. PV is changing so rapidly that it doesn't seem fair to not update the thing I try to update this presentation every year. So please, if you feel that the questions didn't follow the presentation, we need that feedback, and I know my friend at PDH will get with me. We'll make sure that you've got questions that fit in with the slides that are presented. You probably all had that same experience that sometimes you lift a file and by golly, that file name is the same as the previous file, and they end up getting the wrong set of plans or whatever the wrong might be. Okay, well, let's see, time are we? 4:03, we've done 2 hours and 2 minutes. That should be fair. Okay, well, I am going to watch the participant count, and I'm going to stay online until it goes down. There is a little button you got to press to exit, and if you have on top of your screen, if there are 3 dots that say more, then on the bottom of that drop-down menu, there is the red leave button. You know, your leave button may be on a different place on your screen, but if you got a thing with 3 dots in a toolbar, then go to the one that says more and click the leave button. I see folks are finding it. Okay, and I hope you enjoy. Happy Halloween to everybody, by the way. Some of you may be somewhere near Salem, Massachusetts.